This is Breanna McGowan from my Lab 7 Part 1 at-home video report, and it is on the lab with the black hole mass. My main objective was to use the data given in the CSV file and to observe the motion and use the information to determine the mass of the black hole. I was also aimed to analyze relationships between the different forces and the changes in momentum. My main results were that by applying Newton's gravitational force principle, I could determine the mass of the black hole. And then through my observations, I could see the connections between the different F-net components and the change in momentum components, which is essentially that the net force caused the change in momentum. So I had to input all the quantities of the mass of the star and the position of the star, given where the position of the black hole was relative to it, an origin position, set the time to 1 day, and put in all the data positions by entering the CSV file. So here you can see I have all of the information in its respective positions, and I can have it all set up so it'll run properly. This setup also includes putting in the proper net forces and changes in momentum by applying concepts such as momentum principle, the different force components on different axes, like the parallel and perpendicular components. And I also had to set the arrows so you can know the black is the net force, the blue is parallel net force, and the red is perpendicular net force. This is all shown here under the calculation loop. So now I'll go ahead and show you the model. Here's a star orbiting the black hole, and here's the parallel component of the net force, which is blue, the perpendicular component, which is red, and the total net force component, which is black. This bottom line here, which is the F grav equals gm1 m2 over times r hat over r magnitude r squared, rearranged so that is equal to the mass of the star. I was able to print the mass of the star, which was, the black hole. The mass of the black hole is 3.95 times 10 to the 31st. So going back, this is the model and all the force components. Now, what does this all mean? So with my analysis, I first thought about the net force and how it's the perpendicular component plus the parallel component. And the momentum principle, momentum equals magnitude of the momentum times p hat, and the rate of change of that is simply the derivative form, and so you have dp dt perpendicular plus dp dt parallel, which you can see exactly what that means right here. And essentially the parallel components are the magnitude of the motion on the axis parallel to the motion. So dp dt, the change in momentum parallel component, is the observed magnitude of the motion. The net force parallel component is the sum of all the forces on the axis parallel to the motion. So the net force causes the change in momentum, and it can be calculated from the change in momentum. They're not the same thing. It's a similar story to the perpendicular components as far as that the net force causes the change in momentum. And if you don't have the net force, you can use the change in momentum to find the net force. So the change in momentum is the observed change in momentum on the perpendicular axis to the motion, and the net force perpendicular is the sum of all the forces on the axis perpendicular to motion. Now suppose a different black hole was placed in the same location. If the motion of the star was unchanged and it was only affected by the gravitational force on the black hole, could you find the value for the mass that is different from the original mass? No, you couldn't. You see here the equation, and if the motion of the star being unchanged means that the data points were the same, then there is no alternative gravitational force available to calculate a new mass of the black hole. Now, if the motion being changed means it's a similar path but different points, then you could, but that is not the situation we see here. Thank you for watching my video. I hope that you enjoyed it and learned something.